Good afternoon. Hello. Let's get started. How are you all? Day 3, the afternoon of a 3-day conference. Is anyone still conscious? That's a no. Yeah, afternoon of a 3-day conference. I'm wishing I'd gone for a lighter weight topic for this, but I haven't. This is my attempt to encompass the whole of what's going on in programming at the moment, which is a big claim, but I'm going to try. My name is Kris Jenkins. At the moment, thanks to tech layoffs, I'm between jobs, so the most interesting public thing I do is host this podcast. QR code there. Don't subscribe yet. You're going to listen to my voice for 40 minutes. Judge how you feel about my voice after that. That's my advice. I wanted to start this talk, as so many great talks do, with an XKCD cartoon, which in a way changed my perception of the world. I really like this one. If you really hate someone, teach them to recognize bad kerning. Kerning is like the gap between letters in typography. It's like the gap between individual characters. And you've probably never noticed it in your life. Most people haven't. But the moment someone teaches you to recognize bad kerning, you'll see this ugliness of bad kerning everywhere, especially on cheap shop signs. And yeah, Randall's right. Teach someone to recognize bad kerning, and you can torture them on the streets for the rest of their days. In a way, this is a good thing, because they've learned how to make things more beautiful, but you start by showing them how to see ugly things. That's what I'm going to try and do with this talk. So, let's talk about side effects. They're going to seem like a very small thing. I'm going to try and convince you that they're actually a very large and fundamental thing about what's happening in programming at the moment. And I think as programmers, right, we all have, many of us have, a vague notion of what side effects are. Right? Side effects are when you access the database, or when you print the screen or something. That's a side effect, isn't it? Something like that. And we don't really talk about side effects. We don't really think about them. We have a vague notion that they might be bad. We don't have a grasp of what side effects are, usefully, an intuitive, non-academic, day-to-day working definition. So let's start there, because I think they are a big source of complexity in software. So let me put it this way. Every function you write has 2 sets of inputs and 2 sets of outputs. Right? Pair of inputs, pair of outputs. And you say to me, no, Kris, that's not how programming works. I know how programming works. It looks like this. You see? You have a set of inputs, that's the argument list, and then you have a singleton set of outputs, which is the return type, right? One set of inputs, one set of outputs. That's programming. No, there's a hidden set of inputs and a hidden set of outputs, and it's very important. Have a look at this code. This is what's on TV at the moment. Kind of a dated reference now, because everyone just streams on demand. What's on live sports TV right now, right? I give it a channel ID, and it will tell me it will return an option of what program is on. There might not be a program on at the moment, right? There's your set of inputs and outputs. But this code has a hidden pair of inputs, right? It has, can anyone spot it? The current time. Now that is an input to the function. You can't tell me it's not, because the behavior of this function entirely depends on what that value is. It also has another hidden input, which is the list of programs. As Java object-oriented developers, you may feel more comfortable with that. It's part of the state of the object. I'm not going to debate that too much. I think they're both hidden inputs to this function. The behavior of it absolutely depends on those inputs. Having a look at another piece of code. This is some code that's going to delete emails by a regular expression, which is how everyone wants to delete their emails, right? This has an input of the search term you want, and it returns a Boolean, did I delete some stuff or not? Those are the inputs and outputs that are explicit. The hidden input is the state of this inbox manager before you call it. Right? That's absolutely an input to the function. The behavior of this function will depend on the state of that inbox manager. And the hidden output is the state of the inbox manager after you've called delete. It will probably change. So there's an extra output, and none of this is in the type signature. So there's my definition of side effects. hidden inputs and hidden outputs on a function. The bits that it secretly depends on. If you go away with nothing else from this talk, go away with that, you'll be able to reconstruct everything else I'm about to say from that. But you might be saying now, so what? That's programming, right? You have some explicit inputs, you have some stuff we depend on. Isn't that just programming? No, or at least it shouldn't be. It really shouldn't be. Because think about the effect of this on testing. You can't test this code. This code is impossible to test because you have no idea what it actually needs to test it, right? What it really should say is this code actually takes a pair of things on the input and returns a pair of things on the output. You can't test the first function without looking at the source code. And when you look at the source code, you'll realize you need to set up a mock object that behaves the way the inbox manager does. And you'll do that dance. You probably do the dance of a null pointer exception back and forth until you figure out all the stuff you need to set up to get this tested. But I think that first one's a lie. The second one is true. That's what it actually depends on. Now, you may not like that second function. You may not like that second API because you think the one above is simpler. And I would kind of agree with you, except the first one is a lie. The second one is the inherent complexity of calling this function. It's like Albert Einstein said, make things as simple as they possibly can be, but no simpler. The second one is true. So if you can't test the first one without seeing the source code, you can't black box test it. But it gets worse. It gets worse than just our local testing, because you hand that API off to someone else to use, and they can't use it without understanding how to set up the code correctly. You can't just give someone a function signature and say this is reusable code. And what they'll probably do is, again, they'll try and call that function, and it will generate a null pointer exception at runtime, and they'll fix that with the appropriate setter, and then they'll get another one. We've all done that dance in Java, right? Until you set all the setters that mean it actually runs instead of throwing null pointer exceptions, and at that point you hope you've got everything. But the API actually wasn't much use to you. It didn't tell you the full story. Which makes it even worse when you're throwing a library over the wall to other people rather than between departments where they can talk to you. But it goes even further, this problem of hidden inputs and outputs. Because, you know that phrase, favor composition over inheritance? Function composition is supposed to work like this. You have the output of one function which matches up with the input of another function, and you can glue functions together happily to build a larger function. Very neat when it works. But we don't use it much in Java world because most of the time it doesn't work as advertised. And this is the reason. Because it's not just about lining up the outputs and inputs. It's about all the hidden outputs and inputs as you try and compose that function together. We have this whole ocean of hidden bits of complexity, hidden dependencies, hidden results, lurking beneath the surface of our system. This hidden dependency graph, you see it in small systems when you're just trying to compose functions, but you also see it in the much larger system. How many of you have experienced this in software design, where a system gets large and old and maybe a bit creaky, and we say, I can't debug this code anymore. I can't understand why it behaves in this way. We should rewrite the whole thing. And the team eventually agrees on a rewrite, and maybe they choose a better language this time, maybe they choose a better framework or better testing techniques, or maybe they're just more disciplined this time, and maybe the rewrite works. But one of the reasons the rewrite works is you take that hidden ocean of dependency and you refresh it into the folk memory of the programming team. And so that people understand where all those little hidden implicit tricks are. And it works for maybe about 5 years until staff turnover, at which point everyone says, I can't understand how the system works, we should rewrite it. And so the cycle continues. I think that's pretty bad for complexity, and it all comes from hiding things which shouldn't be hidden. But it actually gets much worse than that. The rot of hidden dependencies goes all the way down to our data. And when I first heard about this, genuinely, it kept me awake that night. I'm hoping I can keep at least one of you awake tonight with the ghastliness of this fact. Have a look at some more code. I know it's, I want to say it's Friday afternoon. Emotionally, it's Friday afternoon, right? What does this code print? We've got an array of things, we add cats at position 2, and then we print it out. Of course, it's a trick question. You can assume it's not a null pointer exception or an index out of bounds exception. What does this print? It prints dogs. Of course it does, because threads. Because at some point we gave a reference to things to someone else, and they changed it. And maybe they changed it on a thread, or maybe we just called them a while ago and then called them again, and we didn't realize at some point they were mutating that object. And this is scary when you think about it, because our data, our list of things, has a hidden input. It has the hidden input of the behavior of anyone who has a reference to that object. We think we had a list of 3 things, which was a shopping list. We actually had a list of 3 things, which was a shopping list, and the entire collective decisions about anyone who ever had a pointer to that object. That's scary. Even our data can't be trusted to sit still. It's really horrible. Even our data is broken in programming. And one day, maybe 20, 30 years from now, I want to retire. I want to give this talk on the day I retire and just say it's horrible and walk off stage and leave it there and go and learn watercolors or something. But I'm not allowed to do that. I have to stay on stage and give you some hope. So, what can we do about this ball of mud, about these hidden dependencies? Well, one thing we can do, is a trick we all know, especially as Java programmers, you put a wall around the data, right? You say, okay, I'm not going to give anyone access to this piece of data. I'm going to put a wall around it, and I'm going to have an API, and the only way you can use that piece of data is by talking to me. Right? You federate access. And yeah, we call it encapsulation. Really, it's protection. You know? And then we do this in the large, right? We do exactly the same trick in microservices. Put a wall around your database, data store, data state, and only allow people to access it through an API. It's okay. I'm not saying it's bad. Maybe I'm a little bit. You can kind of get that tone. But it's one approach we do, right? That's one trick. Do we have any other tricks in the computer science toolbox for handling this? Yeah, we do. And I think there's a pattern going on in programming at the moment which unifies a few of these. We're trying to reach the same point via different channels. So one I think is really interesting is Rust. Any Rust fans in the room? Not a one. Well, maybe you'll check it out after this. Yeah, half a Rust fan. Hi, half Rust fan. Rust pulls a different trick to this. Instead of putting a wall around the data and federating access to it, it says, well, let's track who owns this piece of data. When it's mine, only I can change it. If I pass it to you, I lose all rights to look at it, and it's just yours. Right? It's an interesting way of approaching the data can change under your feet problem. Just means that no one else can change it while you're the owner. What if we went further than that? I think Rust, that's all I'm going to say about Rust. I think it's an interesting attempt to tackle the problem in a different way. What if we went further than that, though? What if we said no one can change data? Data's supposed to stay put. Data isn't supposed to have behavior. Data is supposed to just be data. What if instead of having an API that said you can change things and there's no return value, we said you can't change things, it's an immutable list, and the only way to change it is to create a new list based on it. All right? This is gradually becoming a mainstream idea. That data doesn't have behavior. That's what we're talking about when we talk about immutable data structures. Data that doesn't have the behavior of other people that can see it. Some people object to this. They say that sounds horribly inefficient, creating a new data structure every time. Not true. We solved this 25 years ago. We've been improving on it and productionizing it ever since. These libraries work. They're in production in many languages. In fact, I will appeal to authority on this one. This is officially a good idea. Oracle says so, so it must be true, right? Maximum reliance on immutable objects is widely accepted as a sound strategy for creating simple, reliable code. I agree. I kind of suspect that the person writing this doesn't know why. But I hope we all do now. It's because it eliminates behavior in data. It freezes data to just be facts. That's really important in programming. If we do that, it opens up data in a wonderful way. If someone seeing your data can't cause it to have behavior, then I can share my data with you. I don't need to put a wall around it anymore. You can look at my data if you need it for other reasons. I might choose to protect the data for security, password, PPI reasons, but I'm not putting a wall around it just because programming will break if I don't. That's important. Okay, that's data. What about other side effects? Do we have any tricks in the programming toolbox to deal with other side effects? Yeah, there's a really interesting one that you might have looked at university and never since. Haskell. Haskell has some tricks about this. I'm 90% not trying to evangelize Haskell here. Maybe about 10%. I am a bit of a fan. What I'm trying to evangelize is the trick, the idea, the big idea. If I'm going to explain this, I need to teach you a little bit of Haskell syntax. So, consider our function, which is add cats. It takes a list of things and a position you want to put it in and returns a new list of cats. Right? Haskell functions, they don't put the variable names in the type signature. So you just see the types. So we'll strip those out. And then another thing, and I really like this, JavaScript, TypeScript do this, the return type goes at the end, which I personally like. It's how we talk about it, right? This function takes a list of strings and an int and returns a list of strings. And then all you do is some syntactic sugar and you're at the Haskell type signature, right? Add cats takes a list of strings, then an int, and returns a list of strings. That's enough syntax. Stop me if you need a bit of help following it along. Okay, so with that, let's have one more look at our delete by search term function. All right? We've got this function which takes a regular expression and an inbox state and will return a boolean and the new inbox state, right? I looked at this code once I'd rewritten it into Haskell's type signature, and I immediately saw something that bugged me about the API. And this is something I like about Haskell. As an aside, I have a talk about how these kinds of type signatures are a design aid. I'll put a link at the end. One thing, this code really should be returning an optional new inbox, I think. I think it would be neater if we said, I may or may not change the inbox. Arguable, but that's where I'm going because I want you to squint to see Haskell's trick here. Squint as you look at that optional, and instead think to yourself, what it's really doing is returning a new inbox state in the context of maybe I will, maybe I won't. Right? If you look at the function in that light, returning a value in some context, you can see Haskell's trick for tracking the side effects we can't eliminate. It manages contexts in the type signature, and we can define all kinds of different types, all different kinds of contexts. So I might have a function like this, register user, and that says if you give me a username and a password, I can create a user in the context of the side effects that we will need to access the database. All right? Doesn't eliminate the side effect, but at least it makes it explicit. It brings it to the surface where we can track it. And now, once it's in the type signature, we can get the compiler to help us. Have a look at this. Imagine you are sending, you're registering tax with the government. Imagine, I don't know what the government's like in Germany. In the UK, this is science fiction, that you might actually be able to submit an API call to the government. But here's a function, takes a list of transactions, calculates the amount you need to pay, and then takes a user ID and the amount, and will give you a receipt, a government receipt ID, provided you have access to the internet to send it and access to logging to record it, in the context of having those side effects, those ways of changing the world. Now, if I have that, and I write this function, handle tax. I try and combine it into a composite function. And I say handle tax will take a user ID and a list of transactions and return a receipt. The computer will complain. The compiler will say, this isn't right. You've tried to hide a side effect. Because it will notice that you can't call this code without access to the internet and without access to logging. And it will force you to be honest about your dependencies until you've given it the correct type signature, which is this. Now, imagine you wake up one day and the unthinkable happens and there's, I don't know, a security hole in a popular logging framework. Hard to believe, but it does happen, I'm told. Right? Look at this code. I can look at calculate tax payment, and as long as it compiles, I know this type signature is true, so I know that calculate tax payment can't be affected by any logging issues whatsoever. It doesn't use logging. But I know that handle tax will be affected. I can see the impact side of all my side effects. I can see the security risks of... I've got a question. Okay, yeah, so the question is, if I want to debug this code, do I then have to stick like debugging information pickled throughout? The answer is generally yes. If you're depending on a side effect, you have to make it explicit. And I find generally that's a good thing. You don't want to hide these things, you want to surface them, because otherwise you're lying about the complexity of your system. There is, however, a get out of jail free card just for debugging. You can print stuff to the screen. And I think that's a practical decision. Yeah. You can in some languages, like Elm will, I think this is true in the current version of Elm, it will let you use debugging, but it won't let you publish a library to the central repository that uses it. Yeah, yeah, that kind of. Um, we're going to get into that. Yeah. So auditing, maybe leave that one to the end because we're going to say some more about auditing. Okay. So am I coming to a Java conference and telling you to learn Haskell? Mostly no. What I'm saying definitely is that Java has been stealing some really good ideas from functional programming, and I think they all line up around this idea of making inputs and outputs explicit, making data just data rather than something with hidden inputs and outputs. And I think personally, the idea of using the type system to track side effects, to track hidden outputs, is a really good one, and I'm hoping that Java will steal this next. But if you want to learn about side effects and really get some great training on the impact of side effects in a system, Haskell will teach you ruthlessly. All right, that's fair. But this is all language level stuff, right? What about larger systems, building larger business systems? Well, let's consider a function. Let's consider a function in the context of calling across systems from my microservice to your department's microservice, right? Have a look at this function. Deposit money to an accounting service, to the Alice user, 5,000 arbitrary money units. The exchange rate is about 1 these days between dollars and euros and pounds, so we'll pretend. Hopefully you can guess my favorite argument in this function by now. My favorite argument is 5,000, because it's just data. It doesn't change. It's just an immutable piece of data. It's a number. I like that. I kind of wish we could do the same trick with Alice. I want to get rid of all the side effects, all the hidden behaviors in this data. My next target is Alice. To be honest, I probably would have made this change before I learned about side effects. I'd probably change it from the object, which is mutable, to some fixed ID. So Alice user ID. I'm putting in the string there for illustration, but it would just be a fixed user ID, right? And I think that's... Can we go any further? We've eliminated the side effects in 2 of the arguments. Can we actually eliminate the 3rd one? You might reasonably say, no, we've kind of got to call this accounting service and we expect it to change state, right? We don't really have a choice. Except, of course, we do, because I'm begging the argument. Testing points us to a fact that we can do something about this. Because like the earlier code, if we try and test this code that ends up calling deposit money, I think we'll set up a mock object which represents the accounting service, and we'll try and give the mock object all the behaviors that matter for that accounting service. I actually think by testing this code, we'll probably spend more time writing the mock accounting service than we will testing our code. It's a common anti-pattern in unit testing. So that tells me that this code is depending too much on the behavior and state of the accounting service. We're not really testing this code. So what if we did the same trick we just did with Alice? What if instead of passing the object as an argument, we just said a fixed string? We just said, here's where you can find the accounting service. And we just called it with that. In fact, what if instead of calling a function, we just emitted a data packet that says what we want to happen, who we want to do it, and what the arguments are, right? This would be testable, undeniably. This would take immutable data as an input explicitly and return immutable data as an output explicitly, and we could test it just like a pure function. It would be great. If we built a system like that where someone else worried about the delivery and invocation, we would have eliminated side effects. We would have also accidentally implemented the actor model, or a big chunk of it. Right? We would have independently discovered actors. Write the data. Don't call the function. Write the data. Throw it over the wall. Someone else's problem. And you would end up with a programming model that looked quite a lot like this. Just from the point of view of the actor receiving stuff, it just gets a series of facts, data packets, events, bits of information that it has to act on. It will change its local state somehow, and it might emit further facts, bits of data, events to go downstream to someone else. And this is actually a universal programming machine that we've known about for, hang on, do some maths in my head. I think we've known about it for about 70 years. If I show it to you in type signatures, it might be clearer. Here's the Java version. This is the Java version. I'm going to show you the Haskell version as well. I personally think it's a little more readable. A universal machine takes an immutable copy of its old state and some interesting fact that's just happened and returns a new state and maybe some new facts. That's a pure function that can model just about any machine you're interested in. We've known this for decades. We could build our systems like that, and we would end up with just a series of pure functions that transform one stream of facts into another stream of facts and a bit of memory, right? Has that got rid of all the side effects? They're almost all explicit. There's one in there that I really don't like, which is if the system goes down, we lose that pending inbox of facts, right? I don't like the side effects of have we crashed recently. So let's deal with that. Let's make it a persistent queue. That's my worst pun in this deck. It's really bad, isn't it? Okay, so we put it on a persistent bed, right? We've got queue. We've gone from actors to queues. Is that the model I want? Almost. Machines as pure state transition functions, facts as pure immutable data going between. The only thing I don't like about this is these things falling off the end, right? That's unnecessary mutation of the queue. And I think I can actually make this a bit simpler. Instead of using a queue, just write it down on the append-only log. Write it to a file. There's no reason to delete data just because this machine has processed it. Just stick it in a file. Appending to a file, it's about as side effect free as we can manage. It's super cheap. Appending to a file is about the cheapest file operation you can do. We can build any programming machine we like from that. Yeah, that I think is as pure as we can get for a machine. And chances are you're already using this. as a programming model. If you've ever used Java streams and called reduce, you're using this programming model. You can use this anything from small code like that up to microservices. Chances are, if you've got a relational database, this is how your relational database works these days. Every time you issue a query or an insert or an update, the first thing it does is write it to an append-only event log. Then it updates its state machine to the next. And the great thing about this is if the system crashes and it loses its database, it can just reconstruct it from this list of facts. And you can copy this list of facts to another machine and get an exact replica. And you can copy this list of facts to another machine and get perfect testing data, which you can then test reliably because it's just data in, data out. And another thing you can do with this is you can then come along and look at this list of facts that you've recorded for one programming purpose and build other machines that look at the same facts for different reasons, like auditing. Like the marketing team comes along and wants to do some analysis on user behavior. You can build multiple machines reading the same easily accessed, unfederated data, because it's immutable, and share it around the teams to be interpreted for different purposes. And if we do that, we've kind of invented Kafka and event systems, just by trying to eliminate effects. Just by trying to make things as pure functions as possible. We've invented Kafka, event systems, and if you zoom out a little bit, we've kind of invented the idea of data meshes, if you're interested in those. It's a simple, reliable programming model that's explicit about its inputs and outputs. It works in the small, it works in the large. We're gradually stealing it from functional programming. We've been using it in user interfaces. Increasingly, if you know Elm is entirely based on this idea. If you don't, React and Redux stole it. Not stole it. Stealing ideas is fine. Picasso says so. But was inspired by it heavily. I think they could have pushed it further, honestly. But this is what they're trying to do. Data comes in, a transformation, more data goes out. Easy, simple programming model. So let's talk about side effects one last time, right? There was this paper called Out of the Tar Pit. It was published in 2006. I have some issues with this paper. I'm not wholly endorsing it. It's a bit too optimistic about how much programming business people want to do and how good they are about being explicit about what they want. But it has a really good clarifying idea. It says what we do in programming has a combination of inherent complexity and accidental complexity. Inherent complexity is, I want to calculate someone's taxes. Well, the government decides what the rules are. There's nothing you can do about that. You can't simplify that any further. That's a complexity that's inherent to the problem. Accidental complexity is all the mistakes we made in over-engineering and hiding and fudging our programming. All the things that we do to get around limitations of memory or disk space. All the things we try and hide beneath the surface of the problem to pretend they don't exist. We sweep them under the rug. And I think if we just look at the world as a series of hidden inputs and hidden outputs, and try and surface those explicitly into the type system, into the design of the system, we can at least see what we're trying to tackle and begin to eliminate it. That's the fundamental thing I want to leave you with. So, more practically, what do I want to leave you with? If you just remember that side effects are hidden inputs and hidden outputs, you'll start seeing them in your code, I promise you. You'll start seeing them in your code, you'll start seeing them in the design of your systems, and I hope they, like bad kerning, become grit in your eye, because it will change the way you're programming. If you haven't already, please look at immutable data structures, because I think the worst side effect is the fact that data itself doesn't sit still. And have a look at Haskell if you want to be trained to spot side effects. Have a look at actors if you're finding you're setting up too many mock services. And having looked at actors, look at queues and then have a look at immutable logs. Like Kafka, Red Panda, things like that. Most of all, don't have nightmares. Thank you very much. That QR code has a link to my podcast if you're not sick of the sound of my voice. It has a link to a really good book called Designing Event-Driven Systems by a friend of mine, Ben Stopford, which will teach you how to... It doesn't talk about side effects, but it talks about this universal immutable facts traveling between different systems architecture and how that plays out in the real world. And there's a link to a talk I gave a while back on using types as design tools if you're interested in that. And my contact details if you want to get in touch. Everything. QR codes are great. Boom. Anyone got any questions? Anyone completely mentally exhausted by that whirlwind tour of programming? Thank you. Question? If you want to get started in a practical way, that's a really good question. So definitely get used to programming with immutable data if you're not already. That will open your eyes to how vulnerable your data is. And then probably the easiest thing for most of the people in this audience is to start trying to learn to model things. Instead of modeling it with mutable objects, try modeling things with immutable data going through stream transformations. That will teach you a pattern that works in the large and the small. If you're interested in learning Haskell, it's great brain food. You might also consider Elm, which is a more user-friendly implementation of the big ideas. Or Unison. Unison's very interesting. Got a podcast coming up on that in a couple of weeks. And that's in a similar space. Probably Haskell, but a bit more user-friendly. Haskell is probably the one that's going to get you closest to production, if you can believe that. I've been a contract production Haskell programmer. We've built some great systems. It is possible. If you want to do it in the large, consider looking at actors and queues as a way of communicating between your subsystems. Yeah, that's my practical advice. I don't think there are any more questions. Thank you very much. Cheers.